Welcome to Infinite Mathematics. This will be our first video covering the Advanced Functions Pre-Calculus course content, and today we'll be discussing functions and their properties in just a basic introduction and some review of some concepts. So here's my best attempt at sketching a parabola and the graph of y equals x cubed, and we'll be reviewing some concepts such as domain and range. So we'll do the domain and range for this parabola here. So just to review, domain is the set of all independent variable values, so all the values that x may take up. So if we look at the graph of x squared, well, x being any real number, we can square any real number. We can square an integer, we can square a rational number, irrational, we can square 0, we can square negative numbers, we can square anything. So we can say that the domain of this function of y equals x squared is just all real numbers. So x belongs to the set of real numbers. And the range, well, any number squared is always positive, or it can be 0. If you put in 0, 0 squared is 0. So any number squared is always positive, or it's 0, and that makes sense graphically because the graph is always on the x-axis or it's above the x-axis, so it's always equal to 0 or greater. So we can say that the range is y is any real number as long as it is greater than or equal to 0. So now let's talk about a new concept, symmetry. So symmetry is either defined as odd, it's defined even, or it's neither. So let's first examine the graph of y equals x cubed. So if we look at the point here, which is 1, 1, and then we look at the point negative 1 and negative 1, which is here, it's not very accurate, but you'll see that if you were to compare the distance from negative 1 to the origin, and the distance from the origin to 1 and 1 is exactly the same. So the distance from 0, 0 to the point negative 1 to the point 1, 1 is this exact same distance. So we can do this little thing here. So we can say that this distance x and this distance x are equal. So these points are equally spaced out from the origin, and so any function that has symmetry like this about the origin is called an odd function. And algebraically we can show this as f at negative x is equal to negative f at x. And that makes sense because if we do this for the function y equals x cubed, which is if we plug in f at negative x equals negative x cubed, negative x cubed is negative x cubed, and so f at negative x is equal to negative f at x. So that means this function is odd. And also another interesting property of odd functions is it has rotational symmetry as well. So that means if you were to turn the graph 180 degrees in any direction, clockwise or counterclockwise, you would end up with the same graph. That means if you can either say 180 degrees or you can say turn the graph 2 quadrants. So what that means is if I take this graph here and I turn it into this quadrant, it'll be reflection in the y-axis, right? And then if I take it from that quadrant and I shift it over here, I'll have the exact same graph that I have right now. So if I turn the graph 180 degrees or 2 quadrants, it doesn't matter which direction, I'll end up with the same graph. And any function that has that property is called an odd function. So we can say y equals x cubed is an odd function. And so what about an even function? So an even function, an example of an even function is y equals x squared. So any function that is symmetric about the y-axis, that is every coordinate is evenly spaced out from the y-axis is an even function. So on a parabola you have the points, this isn't very accurate, but you have points like you have 2 and 4, and then you have negative 2 and 4, because 2 squared and negative 2 squared is always going to be positive 4. So you'd have the point negative 2, 4 here, and then the point 2, 4 here, and they would be equally spaced out from the y-axis. So any function that has that property is an even function, and algebraically all even functions can be written as f at negative x is equal to f at x. So whether you take the positive value of x or the negative value of x, you always get the positive result. So f at negative x equals f at x, and that makes sense if you plug that into the equation for y equals x squared. If we do f at negative x equals negative x squared, any number squared, positive or negative, is always positive. Negative x squared is x squared. So f at negative x is equal to f at x. And so we just proved that this function is even. And a function can be neither. So if you test it using f at negative x, and if it doesn't equal f at x or negative f at x, then that means the function is neither. So now let's talk about end behavior. So end behavior, it's also a new concept. End behavior is simply the description of f at x as x approaches really large positive or negative values. So what I mean by that is, well, if we look at our x values here, so this is 1, then it goes to 2, and 3, and then it goes all the way to infinity. And then the same in the opposite direction, it goes -1, -2, -3, and it goes all the way to negative infinity. Well, let's examine the graph of y equals x squared. So as x becomes really large, as x goes to infinity, what happens to the y values? Well, we see that as x becomes infinitely large, the y values also become infinitely large too. As x approaches positive infinity, the y values go to, say, 2, go to 3, 4, and then they go to infinity. So we can write this as x approaches infinity, y also approaches infinity. And if we look at the other direction, as x approaches negative infinity, well, y is still approaching positive infinity. So we can rewrite this as x approaches positive or negative infinity, y approaches infinity. And that makes sense, because whether you plug in a positive number or a negative number, the result will always be positive, because any number squared is always positive. So whether x approaches positive or negative infinity, y will always approach infinity. And then let's talk about the intervals of increase and decrease. So the intervals of increase and decrease are basically intervals of the domain where the function is increasing or decreasing as you look left to right. So if we look at the graph of y equals x squared from left to right, well, if we're coming from negative infinity down to, say, 0. So we look at the graph, we're going left to right, we're at -3. Okay, at -2 the graph has decreased more, at -1 it's decreased even more, and at 0 it's just neutral at one point. So the graph was decreasing from all the way from negative infinity to 0, and then from 0 onwards the function seems to be increasing. If we look at 1, the function is at 1, at 2 it's at 4, at 3 it's at 9, at 4 it would be at 16, and then as x would approach infinity, y would approach infinity. So the function is decreasing from negative infinity to 0, and this is how we use our interval notation. The function is decreasing from negative infinity to 0, and let's not confuse this with coordinates, because that's also how we write our coordinates x, y. But this is an interval, and then this is where our function is decreasing, and our function is increasing from 0 all the way to infinity. So our function is increasing from 0 to infinity, decreasing from negative infinity to 0. And that's pretty much it for an introduction to properties and characteristics of functions, and I'll see you in the next video.